Hello? Hello, sir? Hello? இப்போ கனெக்ட் ஹலோ ஆன் பண்ணியிருக்காரு. ஹலோ சார். ஹலோ, கேன் யூ audible?
Oh yes, I hear your voice.
Yes sir.
Can you hear my voice?
Yes
okay.
Sir, yes sir.
Okay, but your voice is not clear. Okay, anyway,
okay,
we can start?
Yes sir, we can start sir.
Okay.
Hello.
Good afternoon, everyone. Let's start our next session. Now, I would like to call Gifty Zanita from 3rd BSc Physics to the stage, who will share a few words about our speaker, Dr. Mani Govindaswamy.
Warm greetings everyone. Dr. Mani Govindaswamy is a highly accomplished researcher and academic currently serving as a division director at the Research Center for Intelligence Medical Devices at Ming-Chi University of Technology, Taiwan. With a strong academic foundation and extensive experience in nanotechnology, biomedical engineering and electrochemical biosensors, Dr. Mani has established himself as a leader in the field of innovative medical devices and energy storage technologies. Dr. Mani holds a Ph.D. in Energy and Optoelectronic Materials from the National Taipei University of Technology, Taiwan, where his research focuses on the fabrication of electrochemical biosensors for food safety and clinical analysis. His innovative research has led to the publication of more than 200 peer-reviewed articles, garnering over 6,000 citations with a H index of 46, reflecting his influence and thought leadership in the scientific community. In his role as a mentor, Dr. Mani has guided 15 PhD students, 3 master students, and over 30 internship students, while actively reviewing more than 300 research articles for leading journals. His research interests include the synthesis of nanomaterials, the development of high-performance energy or chemical devices, and real-time applications in biosensors and environmental monitoring. Dr. Mani has received numerous accolades for his research excellence, including the Outstanding Research Award from the CTCI Foundation in Taiwan, and he frequently collaborates with international research institutions across Japan, India, and South Korea. His contributions extend to editorial roles, serving as a guest editor for Frontiers in Chemistry and the Journal of Electrochemical Society. With a passion for mentoring young researchers and advancing cutting-edge technologies, Dr. Mani's insights into the future of biosensors and energy conversion devices promise to inspire and enlighten today's audience. This introduction highlights his expertise and impact while making it suitable for a professional speaking engagement. Thank you.
An investment in knowledge pays the best interest. It gives me immense pleasure in welcoming Dr. Mani Govindaswamy, Assistant Professor and Division Director, Ming-Chi University of Technology, Taiwan. Over to you, sir.
Yeah. Thank you for your introduction about me. Can you hear my voice? Is clear, right?
Yes, sir. We can hear you.
Okay. Okay. Good afternoon, everyone. So today I would like to explain about my research work and related with 2D MXN based layer materials for clean energy applications, in particularly supercapacitors. So in my research group, we are working on different applications based on the nano materials. In particularly, we are working on 2D layered nano materials to apply for biomedical applications as well as green energy applications related with the supercapacitors and hydrogen productions. So today we will discuss about the 2D layered materials, how we can apply for different biomedical applications and green energy applications. That's my research profile. So first of all, I introduced related with the Taiwan culture and even my Mingxi University. So Taiwan, I think most of the students and our Indian people will know the Taiwan. It's middle of Japan and China. It's one of the smallest country as island. So this one, most of the Taiwan economic is related with electronics and electrical and electronics related with so and the Mingxi. So Mingxi University of Technology, it's like it's like the private university, but in even though it's private university, it's the first sector in the apart from the heavy private institution in the academic institutions. So in particularly Mingxi University, we are focusing on commercial products, for example, related with electronics, electrical, and commercial application aspects. We are developing academic and industrial projects. So this is the university ranking. So this is my research profile. So far my research group, we have published more than 180 publications and review research articles and book chapters and patents and research awards. This is the graphical citations related with the international journals. So in my research group, we are developing different kind of research. For example, 2014 to 18, we developed for biosensor applications, and then we started the additionally supercapacitor in 2019, and 21 we started the sodium-ion battery, and 22 we additionally started the photocatalytic degradations. So far, we worked on hydrogen production and supercapacitors and biosensor applications. Particularly in my research group, we are working electrochemical related applications based on the different kind of nanomaterials, in particularly 2D and 3D nanocomposites. For example, we are developing 2D materials and then we can combine with 3D nanomaterials. For example, matrix related like graphene, MXN, layer structures we are developing, and then we can combine with some metal oxide, metal sulfates, metal nitrides. Then we can move for different kind of applications.
Hello, sir. Sir, your slide is not changing, sir.
Slide is not showing.
Slide is not changing, sir.
Right.
Yes, sir.
Okay.
Yeah, it's okay, sir. Sir, can you do it in full screen, sir?
Right.
Okay, sir.
Can you see my slide?
Sir, it's not in the full screen, sir.
No. Now?
No, sir.
Why? Now okay?
Yes, sir. Yeah, sir. It's in the full.
Okay, right?
Yes, sir.
Okay.
Okay, sir.
Okay, sorry. So some technical issue. So this is my outline of my research. We have developed the different kind of biosensor applications in 2014 to 18. Then step by step we developed for electrochemical different applications. So far we are working on biosensor supercapacitors and HER and OER related applications. Yeah. we are developing the two, majorly we are working on two different applications. One, the green energy related applications and biosensors. In biosensor, we are working, for example, microfluidics coupled electrochemical biosensors, for example, cancer biomarkers and cancer related research works, for example, how we can find out the early cancer detection, so related with biomedical application we are developing, as well as we are focusing different kind of commercial products related with biological applications and even green energy storage devices. So far, for biosensor applications, we are developing the majorly to biomedical and food analysis. For example, biomedical, for example, biomarkers and cell detections and access to trust biomarker detections and neurotransmitters. So these are the biomedical aspects, and the food-related analysis for feed and food additives and toxic chemical detections in waters and environmental resources and pesticide detections. And then mainly we are focusing on energy storage devices for supercapacitors and water splitting and water splitting for hydrogen productions. For example, based on the 2D and 3D nanomaterials. Basically, so it's well known for supercapacitors. So supercapacitor derived from the capacitors. So capacitor we can use for electronics, electrical applications. In particularly supercapacitor we can develop for various applications. In particularly, for example, vehicles, high transport devices using for supercapacitors. So in particularly supercapacitor, basically we need to know about electrical double layer capacitance. We can say the EDLC. EDLC means it's, for example, we can the charges, it will be separated as negative electrodes attract the positive ions. Similar like positive electrodes will attract the negative ions. In the electrical solutions, for example, it will be in the ionic solution, it will be separate the charges, and then it will be forming the Helmholtz double layer. It will be separated as the two different charges. So that the part we can say electrical double layer capacitance. So based on the EDLC, we can think about how we can store the electrons and how we can get the energy. So similar like EDLC depends on the carbon related materials, and pseudo supercapacitors the second one. So we can develop the pseudo supercapacitor based on the metal related materials. For example, metal related materials, we can develop the pseudo supercapacitors, in particularly redox property. So when we can apply for different kind of metal and metal oxides, we can get the oxidation reduction the performance. So based on this, we can calculate the energy storage. For example, this one we can say Faraday supercapacitor. So Faraday means when we can get the oxidation reduction peak current compared to the EDLC capacitance. We can store the electrons. Third one is hybrid supercapacitor. For example, most of the current research work is moving on hybrid supercapacitor. The reason, for example, only the EDLC mechanism. For example, only EDLC means we can develop only for we can enhance only power density. But when we can move for the hybrid supercapacitor, we can enhance power density as well as energy density. So that's the motto we are developing on hybrid supercapacitors. So hybrid supercapacitor we can use for one electrode for carbon related materials, another electrode for metal oxides, metal sulfides, metal related redox property materials, for example, Faraday supercapacitor. So when we can develop the hybrid supercapacitor, we can get the high energy density as well as high power density. That's why we are developing the hybrid supercapacitors. So usually the hybrid supercapacitors and for example common supercapacitor, for example EDLC related materials, most of the materials is carbon related materials. For example, activated carbon, CNF, carbon nanotubes, and graphene related materials, and reduced graphene oxide. So these kind of carbon related materials we can develop for EDLC related mechanism. The second one, pseudo supercapacitors related with bimetal oxides, conductive polymers, and metal organic frameworks. So conductive polymer means not only conductive polymers in presence of metal oxides. So these kind of composites we can develop for hybrid supercapacitors. Then pseudo supercapacitors, and then hybrid supercapacitor when we can combine both. For example, activated carbon and then both mechanism. For example, EDLC as well as pseudo supercapacitor, we can develop for hybrid supercapacitor. The purpose of hybrid supercapacitor, we can develop the power density as well as energy density. So when we can develop for power, both, we can use for multi applications. So that's why we are developing different kind of hybrid supercapacitors. For example, when we can go for hybrid supercapacitor, we can enhance the high capacitance, high conductivity, good stability, and for example, particularly transition metal oxide based composites we can develop for multi applications. The working principles is very simple. For example, EDLC, that's the major principle for supercapacitors. As plus we can combine with Faraday concept, then we are developing for supercapacitors. Sorry. So that's why we are developing for different kind of supercapacitors. Yes. And then usually we are in the supercapacitor applications, we are developing for so we are developing for different based on the different substrate. For example, carbon cloth, stainless steel, and nickel foam. For example, we are developing different kind of metal oxides, and MX and related materials. How we can develop the products? So basically, in the research lab, we are using different kind of substrate. For example, carbon cloth, stainless steel, nickel foam, aluminum foil, and for example, graphitic sheet and copper foils. Even many different kind of the flexible substrate we are using. Mostly in my research lab, we are using for carbon cloth as a flexible substrate and nickel foam. These are the substrate we are using, and stainless steel also we are using. Not stainless steel means stainless steel mesh, so it's like very flexible material as well as the flexible, similar like the nickel foam. So these are the substrate we are developing. For example, it's a very simple procedure. So in my lab we are using for different kind of the fabrications. Very similar procedure for we are using some binders. Sometimes we are developing for in-suit material preparation on the substrate, but mostly we are developing for the coating technique to prepare the nickel foam with the different ratio for the carbon materials and active materials, and then even binders we are using to making the electrodes. So, for example, electrode and electrolyte. So, this is the basic concept for the supercapacitors, particularly electrode. So, for example, electrode, what are the properties it is need very specific for the materials, the electrode materials? The main thing, high electrical conductivity and high specific surface area, and chemically and thermally it need more stable. And then, for example, lightweight materials, it's better for when we are moving for commercial materials. So, these are the major properties for electrodes. For example, when we are moving for 2D layer materials, it's almost, it will be very matched with, these are the properties for commercial applications. And then electrolyte. So electrolyte, based on the electrolyte, we can change, when we can move for the wide potential, so we can develop for the high energy density. So even broad potential, and then ionic conductivity, high electrochemical stability, and environmental friendly. For example, sometimes we can even acid related compared to the acid or some other electrolyte, better we can use for KOH or KCl. KOH related, it's more flexible. So for example, compared to the other, it's environmental friendly. So we are using the environmental friendly electrolyte. Even solid electrode we are developing through the different kind of the procedures. We are developing solid state electrolyte. So these are the basic concepts. So usually we are developing for electrolyte for aqueous electrolyte, and then organic electrolyte also we are using, and gel, for example, solid related and gel polymer we are using for electrolyte as concept. So basically for 3 electrode system we are using PT and silver chloride, and for example working electrode as a nickel foam or carbon cloth or stainless steel mesh. So these are the substrate we are developing for 3 electrode system aspects. But when we are moving for 2 electrode system, we are using coin cell and pouch cell we are developing. Maybe later you can see what are the so here for example coin cell assembly mostly we are using for like the commercial, how we can go for the commercial supercapacitor. Similar concept we are developing coin cell assembly. In my lab we are developing, for example, a multi-layer MX and related materials to combine with the anode and cathode. Then we are making for hybrid supercapacitors. So for example, in my lab we are developing for 2.7 volt batteries for commercial. Even it will be have the industrial collaborations. We are moving for commercial application aspects. So, for example, basically we are developing for the flexible substrate using carbon clad. So, for example, and then the second one, the pouch cell assembly, and third one for switch lock. So, switch lock cell, it will be just the prototype switch lock cell. Just we can combine the anode and cathode material, then we can check the performance. But when we are moving to the commercial application, mostly we are developing our coin cell supercapacitor. That's more better than the switch lock cell and even pouch cell. But when we are moving the pouch cell, we can get the higher energy density, and then it will be compared to the coin cell, it will be more surface area, and then we can use for more materials to get the higher power density and energy density. So usually it's very common for supercapacitor applications. For example, supercapacitor application we can use for even the street lights, even renewable energy storages, even for example electrical and hybrid vehicles, and even transport vehicles we can use for different kind of energy applications. So in my lab, we are developing 2D layer materials. Why we need to develop our 2D layer materials compared to other even microstructure, or because the reason the 2D layer materials have the high surface area. For example, layer by layer structure, it have multi-energy storage space. So that's why we are developing different kind of 2D layer materials. For example, graphene. So graphene, you know, right? It's well-known material. It's layer structure. It will be very thin material. For example, it will have the multi-layers we can combine. For example, RG, reduced graphene oxide, graphene, we have high conductive materials, and then you have the high surface area. Similar, like the same concept we can apply, we can develop using MXN. So MXN also, it's 2D layer materials. We can apply different kind of applications. In particularly, for example, environmental and water analysis, clinical analysis, and food analysis, and energy. So we are working these 4 different fields. In particularly, in this section, we can discuss about the energy applications for supercapacitor based on the MXN. So, for example, these kind of, in my lab, we are developing different kind of the 2D layer materials. For example, graphene related materials, and molybdenum sulfide, tungsten sulfide, like this MX2 format. So we are developing, and then 2D layer metal oxides. For example, molybdenum oxides, tungsten oxide, and vanadium oxides we can prepare. Similar, the molybdenum oxide we can prepare as a particle, for example, sphere-like particles. But in my lab, we are developing like the 2D layer material, for example, similar metal oxide concept, but we are developing layer structure to apply for biomedical applications as well as the green energy applications. The reason, for example, 2D layer materials, for example, thermal conductivity is very good, and then large surface area. That's the main concept. When we can go for the metal oxides, for example, sphere or particle, compared to the 2D layer structure, the 2D layer structure have large surface area. When we have developed the large surface area, we can store more electrons, even more ions. We can get the higher power density. So that's why we are developing the large surface area related materials based on the 2D layers. And then high charge carrier mobility and electrical conductivity. For example, when we can develop our MXN or graphene related materials, it have the high electron transfer property. That means the mobility will be very good for the energy storage applications as well as biosensors. In particularly biosensor, we are working in electrochemical biosensor. So electrochemical biosensors, its need related with high, for example, high electron transfer property. And then, for example, based on the material, 2D layer materials have the flexibility, even transparent material. For example, graphene is very flexible material as well as transparent material. So, for example, supercapacitor application, no need for transparent, but it's when we can go for the biosensor applications, transparent also is one of the important property for commercial application aspects. So in my lab, we are developing, for example, we are preparing from the max. We are preparing from the max. MXN we are preparing from the max. So we are purchasing the max. Then we are developing step-by-step procedure to enhance the different layers and interface to get the MXN structures. And then, for example, MXN means, for example, generally we can know the MXN, right? For example, what about the MXN structures? So MXN structure related with transition calcium metals, and then for example one of the carbon or nitrate related materials we can combine. Then the TX related, for example aluminum, so one of the major common for TX. Maybe later we can see the structure of MXN. So MXN usually we can prefer, for example it will be non-toxic and less energy consumption routine for preparation aspect, and then MXN based hybrid material have the electron storage vacancy. So that's why we are developing MXN related materials. And for example max based to different kind of etching process and even chemical, because the MXN we can prefer the different type of way of procedures. For example electrochemical etching techniques or solvothermal etching techniques, and then salt based etching technique. So many type of way of procedures will be there, but each procedure have the different type of MXN it can obtain. For example HF etching is more suitable to get the higher delamination MXN process, but the problem is HF it can compared to the other chemicals it will be little bit toxic. So that's why, so we can even though we are developed, for example so far HF etching is one of the best etching in the MXN preparation, particularly max based to MXN preparations. The HF etching is one of the best method. Then we can go for the delamination process. Based on the delaminations we can get the different it will be enhance the interlayers between the different sheets. Later we can see how we can get the delamination process, and we can go for the electrode fabrications. So electrode fabrications we can develop for lithography techniques or even screen printed techniques, and then even the sol gel coating techniques. So many different techniques will be there. So in my lab we are using some laser techniques, and then screen printed technique we are using, and Dr. plate coating technique. So these are the techniques we are apply for making the electrodes, for example anode and cathode. These are the, for example, commercial application aspects we are developing. Coin cell, pouch cell, and coin cell, pouch cell is more we are developing, but switch lock cell we are checking the performance. So why the 2D MXN? So similar like the large surface area is major concept, and second one is abundant nucleation sites. Nucleation sites means, for example, it will be interact with the metals and metal oxides. Then it can store the ions and electrons. It will be very comfortable. So that's why we can develop our 2D layer materials. For example, layer structure, right? So inside have the interface layers. It can enhance the higher surface area and structural diversity. For example, we can prepare the different layers, and then we can insert the different kind of nano materials. For example, spear-like structures or different kind of layer structures. We can combine with the 2D MXNs. So that's one of the major impact when we are using the 2D MXN materials. These are the concepts we are developing 2D layer materials, and particularly MXN. So these are the methods we are following for preparing nano materials. And MXN usually we are preparing for two different techniques, one chemical etching and second one is electrochemical etching. So these are the techniques we can apply for the metal oxide preparations and metal sulfate preparations, some intercalations techniques we are using. And previously we worked on CVD, chemical vapor depositions. So chemical vapor depositions for graphene preparations. So based on the graphene CVD techniques we can apply for biosensor applications, in particularly cancer biomarker detections we can use for, because the CVD it's one of the unique technique to develop the single layer or multi-layer, bi-layer graphenes. Then we can use for commercial application aspects. That's why we are developing chemical vapor deposition, but it's more expensive compared to when we can go for hydrothermal or sonochemical or sol gel methods. CVD techniques very unique, but the problem is it's expensive. But when we can go for the commercial applications, so we can develop for very thin film, it will be suitable for CVD technique. So laser technique also we are developing. So graphene related materials we are developing for laser related procedure we can develop for graphene substrate. So usually the MXN preparation from max. So max related materials, for example, max means we can, for example, titanium. So in presence of the max, these kind of materials will be there: aluminum, titanium, carbon, oxygen, fluorine. So for example, titanium is very less, but fluorine is the more content in the MXN. For example, these kind of material elements we can exchange, for example, titanium. So titanium based MXN is very common MXN material. Apart from the titanium, we can exchange for molybdenum, copper, nickel, manganese, vanadium, so these kind neodymium, so these kind of elements will be exchanged in the MXN related max space. So not only titanium is the comparatively cheapest material in the MXN in the max space, but other materials, molybdenum, cobalt, nickel also have higher the better performance. Still the researchers, they are developing for max space to reduce the cost of MXN. So then only we are, so far the titanium based MXN is the better material for supercapacitor application in the MXN composites. Even though the performance also is better, the titanium based MXN. For example, Achak etching is the normal technique, and then we can remove the A means, for example, here we can remove the aluminium. So we can remove the aluminium, then we can get the titanium carbide related the more elements. Then we can get the delamination process. Based on the delamination process, we can get the different layers. That means, for example, see here this one is the max space. After the MXN, it will be separated as the different layers. For example, when we can, for example, this process. After this process, we can get like this. So after this MXN, for example, etching process, we can go for one more process for delaminations. So after the delamination, we can get the different structure. Maybe later we can see the procedure how in my lab we can developing for different delamination process. Then we can obtain for the higher interface and higher surface area. So this work in my research group we are developing, for example, MXN related metal sulfide. So usually in my research group we are working metal sulfide. That means the metal sulfide combined with MXN, metal combined with MXN, metal oxide combined with MXN, even for example dope related MXN. So this kind of work we are developing. For example, in this work we used for MXN related molybdenum sulfide as a hybrid supercapacitors. For example, the similar procedure, the Achak etching, the first step. The second step we are used for hydrothermal technique to make the we can combine with metal sulfide. When we can use for the molybdenum precursors and the sulfur sources, then we can go for hydrothermal technique. Finally, we can get the MXN combined with molybdenum sulfide. It like the multi-layer structure of composites. So for example, in this work we got the molybdenum sulfide also sheet-like structure as well as MXN also sheet-like structure. Both the composites, for example, bi-layer sheets, it have higher electrochemical property, particularly energy storage property. So in this work, compared to the other previous molybdenum sulfide related materials, we developed around 1227 specific capacitance. Also the cyclic stability is better. And then in particularly in this work we used for lithium perchlorate, so for example electrolyte. But later we developed for KOH related electrolytes. So in this work we used for, because we tried the different electrolyte, but we improved more stable in the lithium perchlorate. So this one we used for supercapacitor applications. So second one we developed for doping. So metal sulfide combined with the MXN. The next one we develop for vanadium doped titanium carbide. So for example, a vanadium, it will be in suit we can develop for in the MXN preparations. For example, max phase, after we can prepare the MXN, then we use for intercalation for potassium intercalations, then we use for vanadium doping. So these are the process. Totally three processes will be there: the MXN to max and max to MXN, and the MXN to intercalation process, and the next one the doping process. So after this doping, we apply for supercapacitor applications. These are the procedures we apply for the vanadium doping related materials. So we got the for example, max space to MXN, see the interface, the layers will be separated. Then after the doping, we got the like different kind of vanadium doping for different percentage. We have, for example, when we are doping with MXN, it can enhance the higher, even when you are doping the vanadium, you can get the higher energy density. For example, power density depends on the carbon related materials, right? So when we can go for the metal or metal oxides, we can enhance the energy density. So in this work, we develop for energy density using the MXN related materials and using the vanadium doping. So in this work, we develop, for example, the power density 1800, more than 1800, even the around the 10,000 cycles, it will give the 97.8% of the cyclic stability. So in this work, we use for KOH. So previous work, so in this work, we use for KOH. For example, we use nickel foam as a substrate. And then this work we develop for metal oxides, bimetal oxide doped with multi-layer MXN. So our concept we develop for the base material is MXN. Then we can combine with different kind of metal oxides, metal sulfides, doping. So this kind of the process when we can combine with the 3D and 2D layer materials, we can enhance the energy density as well as power density. That's why we develop our bimetal oxide combined MXN as a supercapacitor applications. So this is the synthesis procedure to prepare the bimetal oxide related MXN composites. Similar like etching process, then we can go for the hydrothermal method for molybdenum and cobalt oxide. Then we can combine with the sonochemical technique to apply for composite. So in this work, we develop for the device aspects. For example, every work we are developing in the device, but here the asymmetric supercapacitor we use for solid KOH as a membrane, and then we use for activated carbon. In the one electrode we can use for activated carbon, another electrode we can use for MXN related composite, that means molybdenum, copper oxide. Then we can combine with the device fabrications. So in this device, the power density we have obtained around more than 3,000 watts per kilogram. So this one we can get the even 95% of the cyclic stability instead of 10,000 cycles. And specific capacitance is 600. And then we used for KOH, similar like the previous work, we use the potassium hydroxide. I think so far in my lab we are using the KOH as a standard electrolyte for supercapacitor applications. Also we are developing for hybrid supercapacitors. In particularly, currently we are working on supercapacitors. For example, one electrode we are developing for supercapacitor material, another electrode developing for battery. That means the supercapa battery we are working. So when we can go for the battery concept, so we need to develop the high energy density. So that's why we are developing for supercapa battery related with energy storage devices. So in this work, we develop for the metals, for example, metal cation intercalations using the multi-layered MXN composite. For example, we can combine with CR. So here the CR we can use for energy, power density we can enhance. So even though we can use for titanium carbide, but when we can use for additionally the carbon related materials, particularly carbon nanofibers, we can enhance higher power density. So that's why we develop for composite, carbon related composites for asymmetric coincident supercapacitors. So this is the synthesis procedure. We develop for sodium based intercalated with titanium MXN plus carbon nanofiber as a electrode material. Then we can apply for, and then activated carbon we can use for the another electrode. Then we can make the device fabrication. See? So here the anode negative electrode we can use for carbon materials, and positive electrode we can use for as prepared sodium titanium sodium emexin, sodium doped emexin, and then we can say the intercalations, sodium intercalated emexin, and then carbon nanofiber we can combine as a positive material. So for example, here we can use for the coin cell asymmetric supercapacitor, then we can go for the device application. So here we can get the even multi-layer multi coin cell supercapacitor we develop, and we can get the energy density as well as power density. So this is the procedure we develop for the current collector, activated carbon separator, and then material, and then current collector. So this is the simple fabrication technique for the supercapacitors. Similar materials we can apply for, even we can get the around the 3000 watt per kilogram. So this one is better performance compared to the previous titanium based materials, particularly the titanium based emexin materials. So this work also is around 10,000 cycles, it's more stable, 95.4%. So this one we develop similar like the KOH is the electrolyte. So even we can go for the coin cell supercapacitor, we can use KOH as a KOH related solid state membrane we can prepare, as well as we can use some for example commercial solid state membrane also we are using. But so far we are developing, the concept is 2D and 3D layer materials, but we can apply for different kind of the fabrication technique. Then we can move for we can develop the energy density as well as power density. Currently in my group we are developing MOF related emexin. So far we worked in metal oxides, metal sulfides, metal doped, and even intercalations related emexin composites. So far last year we got the one project for emexin, MOF related emexin for next generation supercapacitors. So we are working on MOF related emexin as a one electrode, and another electrode we are developing for lithium related, that means battery related material we can combine as if we can develop our super kappa battery. So this is the concept we are developing for MOF plus emexin. MOF means the metal organic framework we can develop for bimetal MOF. So when we can go for the, for example, cobalt and nickel, we can prepare a bimetal MOF, then we can combine with emexin. See, the titanium emexin is more suitable for supercapacitors. It can enhance the energy density as well as power density. But when we can combine with the MOF related materials, it can enhance, still it will be enhance the energy density. And then another electrode we can use for battery materials. We can develop the both property, battery property as well as supercapacitor property. That means, for example, supercapacitor means we can enhance only, for example, quick charge and quick discharge. When we can, battery means we can charge time, it will take time, but discharge time also similar, like it will be take time. But when we can develop the super kappa battery, that means supercapacitors and the battery concept, we can store the very quickly, as well as the discharge time it can take time to use long time. So that's the concept we are developing super kappa battery. So that's the project is ongoing. As well as we are using for similar like emexin composites, we can apply for various biosensor applications, even biomedical applications. So in this work we develop for recent publication in ACS. This one ACS applied materials. So this one we develop for emexin related composite for biosensor applications, particularly environmental and water related toxic chemical detections. So this is my research group. So as the research group as a PA, and he's my director of my PhD program, and then the PhD master students and the PhD students. These are the PhD students. Icham is the local PhD student, and the other students from India. So they are working as a research scholar. They are working different projects. Biosensor, supercapacitors, and even biosensor have the different categories we are working. Even molecular imprinted polymers, and then electrochemically. The normal procedure we are developing some device fabrications, and then some students they are working on the few students working on in iteration productions as a different project. So we are working my research we are working the different kind of electrochemical applications. So they are new PhD students. Also in my research group we are taking many TEP intensive project. For example, TEP internship project. For example, this project we can, based on the TEP internship project, we can exchange the knowledge from the other research group. So we are providing the 90,000 Taiwan dollar we are providing for every month. We are providing 15,000 scholarship for 6 months. So in particularly, it will be more suitable for working in India for research scholars. It will be 6 months exchange program. If you are interested, maybe you can apply. Later I can show you some procedures. So another program, the IAP. So it also the exchange program, but it only 3 months program. So but we can provide the almost nearly 80,000 Taiwan, 80,000 our Indian cost we are providing for every month. So 90,000 for 3 months research project. So this is very specific. It's very few. Each faculty we are taking 2 students every year. So this is the TP, the first batch TP internship in the 2024 batch. Almost the 15 students they complete the internship program. And the second batch internship program, 6 students they are doing. So this one the July to January batch, and then third batch. So currently they are doing. They came I think in September batch. So right now they are doing the research work. So far they complete for 1 month research program. So these are my research group outline. So we are taking the many international students, and we can extend the research programs. If you are interested, the students for our India PhD students, if you are interested, you can find the website. So TEP study in Taiwan. So this website, we already given the more information about the how much funding and how long the research period and project details, everything we are already given. So if you are interested, you can find the suitable PI, then you can send the email. So really it will be suitable for your research work. They will provide for complete funding. So living cost, even airfare and everything, it will be covered for 6 months research program. So this is the what's the eligible means. The students, the masters and PhD students, they are eligible to apply for TP internship program, and then we are providing maximum 15,000 we can providing, and then just what are the documents need? Just the CV and research plan for 6 months and transcript and even recommendation letter. So just you can send the email based on the project and your profile. They will send the reply to take the TEP internship program. They will give every guidance to how to get your visa, even every process they will give guidance to join the internship program. So next one, finally the PhD applications. So every year in Taiwan, they will take the 2-time PhD applications. One is the September batch, another one I think the February batch, fall semester and spring semester. If you are interested, you can find the website 2024, for example, Taiwan scholarship. Just you can find the Taiwan scholarship. So this scholarship is very affordable. I think around 80,000 every month they can provide to do the research. For example, 3 years and 4 years research project, they will give the full stipend. So based on your interest, you can find the website. Yeah, thank you. So finally, I want to thank the organizing committee, particularly Professor K. Girija. So she invited me to give the talk related with my research work, and I want to thank the other organizing committee, in particularly the Dr.N.G.P Arts and Science, the college committee members, and the conference chairs. Once again, thank you. So finally, I want to finally maybe we can discuss the Q&A. If you are interested, maybe ask the questions related with my research work. Thank you.
Participants can ask any queries. Thank you, sir, for your insightful speech and for sharing your valuable experience with us.
Thank you. Thank you.
reminder, the upcoming oral presentation will take place right here in Seminar Hall 2 and poster presentation outside the hall. We encourage everyone to stay engaged.
Now we'll begin with oral and poster presentation sessions. Now I request all the poster presentation participants to stay in front of their posters. Poster presenting participants are requested to stay in front of their posters. presentation sessions. I'll be calling out the participants one by one. When your name is called out, please come forward to present. To start with, first we have Dinesh Kumar.
Good afternoon, everyone. My topic is nano-composite 2D graphene synthesized various TMDs of molybdenum disulfate, cobalt disulfate and nickel disulfate as a counter electrode for platinum free efficient dye-sensitized solar cell. Myself, I am Dinesh Kumar, Assistant Professor in Electronics, RVS College of Arts and Science. So the counter electrode is one of the important material that will be the play in the solar cell, dye sensitized solar cell. So it's a vital role in solar cell performance. So instead of we using the platinum counter electrode, we can replacing materials in the TMDs like molybdenum disulfate and nickel disulfate and cobalt disulfate. So it's a replacement of the platinum counter electrode, and we can organic and counter electrodes have been created for dye sensitized solar cells. Due to the chemical stability and better electrochemical qualities, and carbon nanocomposite and molybdenum disulfate have been crucial to the counter electrodes. So I can select the three different type of nanocomposite material with the TMDs. Molybdenum disulfate with graphene and cobalt disulfate with graphene and nickel disulfate with graphene in the dye sensitized solar cells. Some results samples are taken from the different these materials. One is energy dispersive spectrum analysis and Raman, SEM and TEM and X-ray diffraction. So these are the various analysis with these different types of nanocomposite materials. So this is about the electrolyte, which will be the in between the two different types of plates, iodide and triodide. This will be the couple between the two electrodes, and the sensitizer is a port excited part of working process, and then semiconductor conducting band is quickly injected with electrons. So I listed some features of these different types of composite material. So first one is the superior electrical conductivity and catalytic activity, and second one is catalytic excites 3D structure, so which will be promote for electrolyte and reactant transparent and exceptional electrical connection for the exceptional performance of dye sensitized solar cell. So therefore the nanocomposite will be the better performance in the dye sensitized solar cell. So these are the materials for preparing the samples. So three different types of material used in the nanofilms. So first one is graphite powders and sodium molybdenate, and the second one is nickel nitride, and third one is cobalt nitride, and fourth one is thiourea. So the synthesis of the nanocomposite material has two different stages. So the first one is solution preparation, and the second one is hydrothermal process. So we can preparing the solution with the help of sodium molybdate with the thiourea, and adding with 60 ml of deionized water with and also preparing the graphite oxide with the Hammers method. And another process will be the hydrothermal, so which will be at 80 degrees Celsius for 24 hours. So this film named as molybdenum disulfate with the graphene, And another, the samples although we can changing the materials of nickel disulfate and copper disulfate with the graphene. So the composite, the meaning of the nano composite will be the combination of the two different types of material. One is the TMDs and another one is graphene. So we can changing the three different types of TMDs with the graphene material. So these are the different types of layers in the DSE preparation. So the first one is ruthenium based N719 dye sensitized TiO2 film, and the second one is TMDs with graphene. I already mentioned three different types of nano composite. And the third one is redox material. Redox means already Sir mentioned about the redox electrolyte in between the plates. So this is about the different types of layers in the dye sensitized solar cell. So the first one is transparent conducting glass, and the second one is TiO2 nanoparticle, and the third one is organic dye, and the electrolyte between the two different types of plates, and the final one is counter electrode. So we can fabricating the counter electrode with the different types of nano composite, and this will be the minus polarity, and the TiO2 nanoparticle will be the plus polarity. So these samples will be conducting various analysis. First one is XRD analysis. So the XRD is the X-ray diffraction. So this will be very useful for analyzing the pace and the crystalline structure of the samples. So in the crystalline structure will be the 002 plane of the graphene, and other planes will be mentioned here of the molybdenum disulfate. So these are the different peaks are mentioned here. So the three different colors. So the first one is A will be the molybdenum disulfate, the B will be the nickel disulfate with the graphene, and the C will be the copper disulfate with the graphene. So the 002 plane will indicate the graphene peak, and the star mentioned in the graphene, and other peaks will be the different peaks of the TMDs. So these are the various planes that will be reflected in the XRD analysis of the material. So these XRD will obtain the various structure of the different materials. So the first one is molybdenum disulfate with the graphene has the hexagonal structure, and the nickel disulfate with the graphene has cubic pyrite crystal structure, and the copper disulfate with the graphene has nano crystalline structure. So these are the structures will be revealed by this analysis. And the second one is morphological analysis. So morphological analysis will be held by the two different material. One is scanning electron microscopy and the transmission electron microscopy. So SEM and TEM analysis. So in the SEM analysis has three different types of samples are shown. Okay, sir. So these are the different types of SEM images of SEM and TEM and XPS images of the various nanocomposites material. So molybdenum disulfate with in the layered type, and the second nickel disulfate with the crumble shaped, and copper disulfate with the flakes types of shapes. And the Raman spectra So this will be the another analysis of the various samples. So the D and the various level of the samples of TMD's material will be plotted here. So the D and G are the bands, different bands of the TMD material. So A, B and C showed here. The first A will be the molybdenum disulfate, B shows the nickel disulfate, and C shows the copal disulfate. And so this Raman spectra will confirm the presence of the different types of material, graphene and all other materials, molybdenum and nickel and other copal material will be present in the samples. And the another one will be the intensity ratio. So this will be pointed out at here, 1.28, 1.30 and 1.32. So these are the intensity ratio of the material. And another analysis will be the DSC's analysis. So the transition metal disulfide with the graphene. So this will be the schematic representation of the fabrication of DSCs. I already show the layers of DSC's material. So the TMDs with the graphene at the counter electrode, which will be the fabrication of different types of material like nickel disulfate, molybdenum disulfate and cobalt disulfate. So some parameters, values are mentioned here, the photovoltaic metrics. So VOC and JSC and FF. So the short circuit current density, and second one is open circuit voltage and power conversion efficiency and the fill factor. So these are the values of nickel disulfate with the graphene. So open circuit voltage has 748 millivolt and short circuit current density value become 16.57 milliamps per centimeter square, and fill factor will be the 0.72. So the overall the efficiency of the nickel disulfate with graphene has 8.42 plus or minus 0.05%. So this is about the short circuit current density graph of 3 different types of TMDs. Sir? So this is about the overall review of different types of TMD material using in the C is counter electrodes. First one is molybdenum with molybdenum disulfate with the graphene, and the second nickel disulfate with the graphene, and third one is cobalt disulfate with the graphene. So in this analysis, the open circuit voltage becomes 736 millivolt, and the nickel disulfate with the graphene has 748, cobalt disulfate with the graphene has 756, and short circuit current density value has become 15.01 value and 16.57 for NiS2 with graphene and 14.86 of cobalt disulfate with the graphene, and the fill factor becomes 0.67 for molybdenum and 0.72 for nickel disulfate and 0.65 for cobalt disulfate, and the power conversion efficiency becomes 8.01 for molybdenum, 8.42 for nickel disulfate and 7.71 for cobalt disulfate. So overall the performance becomes the nickel disulfate which will be the greatest one in the counter electrode value. So the NiS2 is the one of the best counter electrode for the platinum replaced DSCs. So this is about the conclusion of the overall in the presentation. So we prepared the 3 different types of TMD material in the DSC's application. So XRD will reveal the pure nanocrystalline in structure, and SEM and TEM will equal deposition, and Raman spectra will be the graphene had successfully hybridized with TMD material. So among these 3 different types of material, NIS2 with graphene has good electrical conductivity and catalytic activity, which will be the substitute for the platinum counter electrode, and this will be the good catalytic edge sites, 3D structure, and electrolyte reactant transparent. So exceptional performance and JV and performance, and the current density value and the power conversion efficiency. So overall the best performance has the nickel disulfide, which will be the 8.42 plus or minus 0.05. So this is suitable for counter electrode. Nickel disulfide with graphene is the suitable material for platinum replaced DSCs. Okay, thank you.
I request all the participants to complete their presentation in 5 minutes. Next we have Sastika to present.
Good afternoon all. Good afternoon. I am Sashtika Tripadi from 3rd BSc Information Technology at Sri Krishna Aditya College of Arts and Science, which is affiliated with Bhadyar University. Before I am starting the presentation, can I have all your applause please? Because this is my first international conference. So that I will be more confident. So thank you. So, I'm very excited to introduce EcoCleanse-NV, my project. It's all about cleanliness. So this is my introduction, literature study, technical approach modules, and feasibility and viability demo video and conclusion. So before I'm starting, okay, EcoCleanse-NV is an innovative web platform that designed to develop individuality and communities to embrace sustainable practices aligned with UN's SDG called Sustainable Development Goals. And it combines education, gamification, and also social engagement to promote environmental actions and awareness. So users can access tutorials and participate in waste reduction. And also we are offering users a dashboard. On the dashboard, we can track carbon footprints, the statistical values of carbon footprints that will encourage and that will know about what is happening in the environment, how the carbon footprint value is. And next, the platform strongly emphasizes youth, because young people are the heartbeat of our EcoCleanse-NV, because we are rewarding school students and also college students to initiate the cleanliness and also cleanse the environment. By encouraging the students, we are offering a monthly contest like essays, poems, and also the mini projects. On that dashboard, we are also I'm sorry. We are also like showcasing their names because they will inspire more students like them, and it will be contribute to the environment. And also this is a literature study, eco-criticism and environmental literature, eco-emotions and climate change, youth engagement. And also we are like offering the local, we are tracking the local garbage vehicles, because whenever we are heading to the college or schools, appoda vandittu enna varuna idu varum like garbage vehicles alla varum. So that time we will more suffer. Ena போறதுக்கே டைம் இருக்காது. So அங்க ஆல்ரெடி சேர்ந்துட்டே இருக்கும். So like அதெல்லாத்தையும் நம்ம இது பண்றதுக்காக தான். So we are offering the live tracking garbage. Actually it's also existing, but not இப்ப யாருமே அதை யூஸ் பண்ணிட்டு இருக்கிறது இல்ல. And also technical approach. I am using JavaScript for client-side and server-side development, and HTML and CSS for structuring and styling web pages. And frameworks and libraries, I am using Man's technology, M for MongoDB, and then E for Express.js, and R for React.js, and R for React.js, and N for Node.js. For drive tracking location, I am using a Google Maps API, and cloud service we are using FBI. So I would like to show one video which Anna, how to on this? Sir, 1 minute, sir, please. Sir, 1 minute, please. Volume.
Our goal is to engage people to take action in ways that support a clean and healthy environment.
But how exactly? What does it do?
Well, first off, we made it fun. We created waste segregation games for both kids and adults. It's a playful way to educate people while scoring points as they learn to separate waste from everything. Imagine kids teaching their parents too.
That's genius. Kids teaching parents. I love it. What else?
We've got tutorial videos that give step-by-step guide to waste segregation, and with the practical minded, you can track the live location of your garbage collector. No more wondering if they'll show up.
Wow, that's so handy. And what about keeping the streets clean? I know some areas struggle with that.
Absolutely. People can raise their complaints if the neighborhood is moving. We'll make sure it gets addressed. We want everyone to live in a clean environment, and this feature empowers the community to take action.
I love how this involves the community. But what about reducing pollution? It's such a big issue these days.
That's why we're encouraging people to use public transport. And here's the cool part. They can upload their tickets on the website at their ones. It's our way of rewarding environmentally friendly choices.
That's brilliant. Points for doing the right thing. I've been hearing a lot about carbon footprints lately. Does your site address that?
Absolutely. Right on the homepage, we show the carbon and water footprints of users. It's a constant reminder of how our actions affect the planet. We want people to be aware so they can be more responsible.
You're really making people think. This sounds like something that could inspire a whole new generation. You involve students.
Oh yes, we're
would like to conclude this presentation by saying, and we are also offering job opportunities for the household, like housewives, and also many people who are producing the organic products. Recently, Honorable Prime Minister Narendra Modi ji also, like, we are a plastic made up of dress. It's 40% of the dress fabrics is recycled plastics. So I am encouraged by saying this point. I would like to conclude. EcoCleanse is a groundbreaking platform that integrates education and gamification. I thank you. Together, we cleanse our planet and make it greener. Thank you.
Thank you, Jastika, for your presentation. Next, we have Vincent Raj to present.
Good afternoon, everyone. Myself, Vincent Raj, second MSc Physics from Tyagaraja College, Madurai. So my project title is Modeling and Simulation of Refractive Index-Based FPG Sensor for the Detection of Blood, Adrenal, Cervical, Breast and Skin Cancers under the guidance of Dr. N. Srinivasan, Research Dean, Department of Physics, Tyagaraja College, Madurai, and Dr. Preeta Sharan Madam, Associate Professor and Research Dean, the Oxford College of Engineering, Bangalore. So it's not working. Okay. So my content of my project is Introduction to Fiberbags Grating. What is Fiberbags Grating? Okay, sir. From introduction. Okay. Fiberbags, first I will tell what is fiberbags grating. Fiberbags grating is nothing but an optical fiber where we introduce a grating within the fiber's core. Grating is nothing but a periodic variation of a different refractive index we introduce within the core's fiber that will act as a fiberbags grating. So fiberbags grating on a principle, it's act like a wavelength filtering. When we pass light into the optical fiber, it reflects specific wavelength, whereas else other wavelengths of lights are transmitted. That reflected wavelength of light we call Bragg's wavelength. The formula for Bragg's wavelength is lambda b is equal to 2n effective capital lambda. Lambda b is a Bragg's wavelength. N effective is the average effective refractive index, and capital lambda is the period of the FBG. Okay, now I designed FPG particular for the cancer cell detection. So many methods for cancer cell detection techniques are there, but I choose FPG because of biocompatibility, high sensitive, massively invasive. So how I designed FPG is fully based on refractive index based FPG sensor. So every material has refractive index. Every blood sample have refractive index. The mechanism of refractive index based detection is we have biosamples of different cancer cells. When I coat my biosample in the FPG sensor, it will alter the total refractive index. When the total refractive index change, the wavelength shift also change. If we see the wavelength shift in the FPG, we can detect different what type of cancer it is due to the different wavelength shift. So I use hours of grating module software to detect designing and simulation of FPG. So the second image will show the designing of optical fiber using the parameters The second image will show the images of the designing of optical fiber. Using the parameters in the software, I will do the grading in the optical fiber. When we do the optical grading in the optical fiber, my FPG is created. So now we see the resultant discussion. So I take first blood cancer. Blood cancer have some refractive index. So I use RSoft to put in the FPG, get the graph between relative power and wavelength. Relative power shows the amplitude of the reflective spectrum. For every cancer, I find out what is the wavelength shift and what is the reflective spectrum. This is followed by every cancer cells. So I find out the reflective wavelength shift 1.44868 for normal cell, and for cancer cells 1.46342. So actually the center wavelength for FPG is 1.55. After placing the blood cancer in the FPG, my center wavelength will vary. This shift can detect me. It tells that this particular value will tell that it's a blood cancer. So if we go to different cancers, the wavelength shift will vary and it will indicate different cancers. So this procedure followed by every cancers. The same procedure followed by cervical cancer, adrenal cancer, and the second diagram will show the normal cell and cancer affected cells. So this normal cell have also some refractive index value and affected cells also refractive index value. So due to the different refractive index, we get the different wavelength shift. Due to that, I can detect different cancer cells. So this is for breast cancer, MCF7. The same procedure is followed. And this is for skin cancer. This is the merging of all cancers. You can see from skin cancer, breast cancer, adrenal cancer, cervical and blood cancer. So all different cancers, it will get a different wavelength shift. So if I get some wavelength shift value, I can detect for this type of wavelength shift, this is the cancer. So due to different refractive index, I get different wavelength shift. So this is the sensing principle behind FPG, and I calculated the total N effective value and resonant wavelength shift in my project. So this is the outcome of my project. So in conclusion, modeling and simulation of FPG were introduced for particularly cancer cell detection, and I calculated wavelength shift as well as effective refractive index for different cancer cells. I noted that when the N effective value increases, my wavelength shift also increases for different cancers. It will increases from skin cancer to breast cancer. Therefore, this FPG will used as a high performance optical biosensor, particularly for a cancer cell. Thank you.
Thank you, Vincent Raj, for your presentation. Next, we have Sanya to present. Now I request Kavya Sri to present.
Good evening. Good evening all. So, என்னோட டாபிக் வந்து facial synthesis of manganese oxide nanoparticles through precipitation method. ஸோ இந்த ப்ராஜெக்டை நான் இப்போ ரீசெண்டாக தான் பண்ணேன், ஃபுல்லாக கம்ப்ளீட் ஆகலை, ப்ராசஸ் போயிட்டு இருக்குது. ஸோ அது வரைக்கும் நான் என்னென்னலாம் கற்றுக்கிட்டேங்கிறது இந்த ப்ராஜெக்டில் நான் இப்போ ப்ரெசென்ட் பண்ண போகிறேன்.